Good morning or afternoon, students. So today we're going to be covering lattice energy. But before we get into that, you are going to be taking the guided notes on your team. So please go ahead and I would do a split screen between your notes and this video. That way you can write in the notes or type in the notes as you go. So here on this slide, this is just some information that you guys would need. You guys can go ahead and maybe take a screenshot of it, use your phone, go ahead and, or if you want, you can write it down. This just lets you know that at room temperatures, covalent bonds, which are usually liquids or gases, that will be at room temperature. If you have an ionic bond, they're usually going to be in solids at room temperature. And then for polarity, remember, mainly covalent bonds have low polarity or they're either non-polar, where ionic bonds are always going to have a high polarity due to the distribution of the electrons. And then it goes on to the formation. So for instance, an ionic bond is between a metal nonmetal, covalent bond is between two nonmetals, they share electrons. On the ionic bonds, they steal, or one takes the electrons away from the other. And then for shape, for covalent bonds, there's a definite shape. Ionic bond, there's no definite shape. For the melting point, so for instance, since covalent bonds are usually in gas form, they are going to have a low melting point, and where ionic bonds are usually solids, they are going to have a high melting point. And then, so what is it? So then you can go ahead and read where covalent bonds, how they share electrons between two nonmetals, ionic bonds, they steal or take away due to electrostatic attraction, and how it's between a metal and a nonmetal. For boiling point, it's the same thing, kind of like melting point, but to where they boil, and covalent bonds would again have low, ionic bonds have high, and then examples of covalent and ionic bonds are listed at the bottom. So what is lattice energy? So we did mention it very little in the beginning or like the middle of the year, where a lattice is this type of structure here. So this is a lattice structure. So for instance, salt, NaCl, is in lattice form. So that means they're more in an organized form. They're usually solids. And what lattice energy is basically the amount of energy required to overcome the ionic attraction. So keyword is ionic, and it's between oppositely charged ions in a salt crystal or lattice. And it's important to know that the units are in kilojoules per mole. So basically, how much energy are you going to need to separate the sodium ion and the chlorine ion? That's what the lattice energy would be. What type of bond is sodium chloride? So I know that sodium is a metal because it is on the left side of the periodic table, and chlorine is a non-metal because it is on the right side of the periodic table, and it tends to come in a gas form. Now, whenever we have a metal and a non-metal together, that forms an ionic compound, meaning those are attracted together because of the charge. And the force of attraction is caused by the positive 1 charge of sodium and the negative 1 charge of chlorine. And we always say that opposite charges attract. Now, let's say we were trying to look at different charges from different atoms. We would have to know that the greater the charge, the greater the attraction. So we have to look at the magnitude. But remember, we're going to use Coulomb's law to determine our charge on them, our potential energy. So Q, if you remember, Q is equal to the charge, and R is equal to the distance. And KE, that is your constant, which is usually always 1. So we would multiply the charge of one particle. So for instance, if we're getting this particle, let's say it was Q1, that's plus 1. So 1 times negative 1 would equal to, so we had positive 1 times negative 1. We multiply them together. That is negative 1 divided by the distance. So usually they'll give you R. Let's say the distance here is 2. And then negative 1 divided by 2, that is equal to negative 0.5. That would be the magnitude of our compound. Now, the greater the magnitude, the increase in attraction. So the greater the magnitude, the increase of attraction, meaning the increase in lattice energy. So what lattice energy is the amount of energy required to kind of like overcome that attraction. So to get rid of that attraction between the two molecules. And the smaller the distance, so the smaller the size, there is an increase in attraction and there is an increase in lattice energy. So now let's look at some examples. So let's look at our main one that we were looking at, sodium chloride, so NaCl. And the first thing we should look at, we always look at the charge. So we have to look at the charge of sodium and chlorine. So let's go ahead and find sodium. Sodium is right here. Sodium, because it is on the first column, group number 1, it has a charge of plus 1. Now if we look for chlorine, chlorine is over here. And if you remember, it's plus 1. I'll go ahead and write them on top. Plus 2, plus 3, plus 4, minus 3, minus 2, minus 1, and 0. These are the charges of them. Now, chlorine has a negative 1 charge. So this is the magnitude of sodium chloride, plus 1, minus 1. Now, let's go ahead and look at, the second thing to look at is the size. Now, because they are on group 3, they have generally the same size. Now, usually when we're looking at lattice structure, we are going to compare two different molecules. So let's go ahead and let's choose a different molecule. Let's choose magnesium. Let's do chloride, magnesium chloride, MgCl. Now, magnesium is here, and chlorine, well, chlorine's still in the same spot. So magnesium has a plus 2 charge. So I'm actually going to write the charge on the bottom because of space reasons. Magnesium has a plus 2, and chlorine has a negative 1. Now, if we were going to look at the magnitude of the charges, magnesium chloride has the greater charge. Yes, even though you were to multiply 2 times negative 1, that equals to negative 2, and we know that negative 1 is greater than negative 2. No, but we're talking about the magnitude. So basically the number. Pretend like those negative charges are not even on there. Right? Pretend like these negatives are not even on there. So 1 times 1 is 1. 2 times 1 is 2. So magnesium chloride would have the greater magnitude. So properties affected by bond strength. So one of the things is a melting point or boiling point. If you looked at the second slide, the second slide, I did talk a little bit about melting or boiling point. So whenever you have a stronger bonds, that means you have a higher melting point or higher boiling point. So for instance, let's say two different substances had two different melting points. Let's say we had a melting point of 100 degrees and then 150 degrees. The one with the higher number would have a stronger bond, meaning it would have a higher lattice energy. The next thing is hardness. So the stronger bonds equals to harder crystals. So the ones that are a lot more solidified would be the one with the stronger lattice. Odor, so stronger bonds means a weaker odor. So ones that you wouldn't be able to smell that much. Stayed at room temperature, so the ones that are more likely to be solids are going to be the ones that have a greater bond, a stronger bond. Now let's look at bond formation. So whenever a new bond forms, energy is being released. The stronger the bond, the more energy that is released. Now, we talked about energy being released in our last unit. So whenever energy is being released, that is an exothermic reaction. Now, for ionic bonds, this energy is called lattice energy because they are in a crystallized structure. So the higher the lattice, the stronger the bonds, which basically lattice is the amount of energy released when bonds form is identical to the amount of energy required to break the bond. So how much energy are you going to need in order to remove those bonds so you can form new ones? So this is how we are going to predict lattice energy. So there's two things that we need to definitely know. One is the magnitude, so bigger charges produce higher lattice energies. So for instance, a +2 charge and a -2 charge produce stronger bonds compared to a +1 charge and a -1 charge. So that is one thing that we need to look out for. Yes, because even though you multiply 2 times -2, that equals to -4, and then 1 times -1 is -1. We know that -1 is technically bigger than -4, but we're talking about the magnitude. So basically, the bigger the numbers. So because 2 is bigger than 1, the ones with the +2 -2 are going to have the stronger bond compared to the +1 -1. And then the next one is the fewer energy levels. So we know the energy levels are the rows on the periodic table. So the results in greater lattice energies. So for instance, lithium and fluorine, they're both on group 2. Let me go ahead and write that down. They're on group 2, both of them, where sodium and chlorine, they are on group 3. Now, the one with the fewer energy levels, which is lithium and fluorine, will have the greatest lattice energy. Main reason because if you were to actually draw out the atoms for lithium, let's say this is lithium, this is the electron for lithium, look how close it is to the nucleus. And if you were going to do the one for sodium, sodium would have 3 rings. Ooh, I drew that last circle a little bit way unproportional. So sodium has 3 rings, but the distance from here to here is definitely a lot greater compared to lithium fluoride. So the attraction, so how much the positive nucleus and the negative electrons, they're way more attracted when they're close by compared to this one here. This is like a long distance relationship over here, and this one, they live close by. So the charge is by far the bigger factor and should always be compared first. So always, always, always we look at the charge first. This is what we look at first. And then we would look at the different energy levels second. Now let's look at our first example. It says, which compound will have the greatest lattice energy? Magnesium sulfide or lithium fluoride? Now, whenever we get a problem, the first thing we need to do is look at the magnitude of the charge. So it says here, magnitude of charge is the first thing we should look at. So we got to find magnesium first. So magnesium is here, and we need to know the charge. Let's go ahead and write it in. Magnesium has a +2 charge. And we look at sulfur. Sulfur is here. Now sulfur has a -2 charge. Now we have to compare it with the charge of lithium fluoride. So lithium has a charge of +1, I'll put it here at the bottom, and fluorine has a charge of -1. Remember, the first thing we look at is the charge. The second thing would be the size. Now comparing the magnitude of magnesium sulfide and lithium fluoride, what do you guys conclude? So we already said that magnesium has a +2 charge, sulfur has a -2 charge, lithium is +1 charge, fluorine is -1. So magnesium sulfide has the greater individual charges. So magnesium sulfide has the greatest lattice energy. Because remember, I told you guys to multiply the Q's, but think about it. You don't have to. If you do that, you're going to get +2 times -2, that's -4, and then +1 times -1, that is -1. But we're not looking at the actual physical numbers. We're looking at the magnitude. So basically 2's are greater than 1. So magnesium sulfide would have the greater individual charges, so that has the greater lattice energy. Let's look at our second problem. Which compound will have the lower melting point? So when we were talking about melting point, now the main keyword is lower melting point. We have to compare sodium sulfide or beryllium oxide. So remember, a lower melting point means we need to select the compound with the lower lattice energy. So first thing we always do is check the charges. So let's go ahead and look for sodium. Sodium is Na, and we need to find the charge. Let's go ahead and write in the charges real quick. Now, sodium has a +1 charge, and sulfur has a -2 charge. Sulfur is right here. It's on the -2 side. Now we look at beryllium. Be has a +2, and oxygen, it's right here, has a -2. So we have +2 -2, and then +1 -2 over here. So you guys tell me, what do you guys think would have the lower lattice energy? Now we said that sodium has a +1 charge, sulfide has a -2 charge, beryllium +2, oxide a -2. Now if we were to compare them, remember we are looking for the lower lattice, so the lower melting point, so we would have to look for the smaller charges. So from here I see this +1 is what would make it smaller. So sodium sulfide has these smaller individual charges, so it has the lower melting point, so lower lattice energy as well. Let's look at this next question. It says, which compound has harder crystals, calcium chloride or magnesium chloride? Now with this problem, if you remember, the harder the crystals, they require a higher lattice energy. So we need to look for the ones that have the greater charge. And remember, charge is always going to be the first thing we look at. So charge goes first. And then second, what do you think it is? That's right, it is the size. So let's go ahead and look at the charges for calcium chloride and magnesium chloride. Let's go ahead and put in the charges first. Now looking for calcium chloride, we look for calcium first. I see calcium is here. Calcium is a +2 charge. Chlorine is a -1 charge. Next is magnesium. Magnesium has a +2 also. And because we're looking at chlorine, chlorine's in the same spot, that is -1. So now I notice that they both have +2 -1. They both have the same charge. So the second thing we need to look at is the size. And if you notice the size, I see that magnesium is on the 3rd energy level and calcium is on the 4th energy level. Both chlorines are on the 3rd energy level. I'm just not going to write that one in. So what does that tell you? So the charges are on the same level, so we have to see which one has fewer energy levels. So if we're looking at the energy levels, we already said that calcium is on the 4th one and magnesium is on the third energy level. So we need to look to see which one has fewer energy levels, and that would be this one here. Let me draw a little star. Magnesium and chlorine together would have fewer energy levels. So magnesium chloride has fewer energy levels, therefore they have the harder crystals because they have the higher lattice energy, meaning there's more attraction between magnesium and chlorine compared to calcium and chloride. And last problem, which compound has a lower boiling point? We have silver nitrate and potassium sulfate. So the lower boiling point means you need to have a lower lattice energy. So if we were to get out the charges, so here I already have them for you. Silver is a +1 charge because remember it's part of the Cad-Zinagle, and I told you guys to remember 2213. So that means silver is a +1. And nitrate is one of your polyatomics. That one is -1. Potassium is on the first column of your periodic table, so that's +1. And sulfate is a -2. But our question's asking which has the lower boiling point, so we're going to look for the one with the lower lattice energy. And remember, the first thing we always compare is charge. Now, if we're looking at the charge between potassium and sulfate, which one has the lower one? It's this one right here, silver nitrate. That means it has a lower lattice energy, meaning it has the lower boiling point. And if they were the same, the second thing we would go into is the size, but we already got it covered with the charge. So that is all for today. Go ahead and answer your exit ticket, and please don't forget to put in the notes. That's it. Thank you. Have a good day.